Hey guys, I wanted to record this video to help you out with the Universal Gates Lab. There are a few things that, let's look at the browser for a minute just to see what we're up against here. So you're seeing a few things you haven't seen before. In 1A, there is a NAND gate that has two inputs, but they come from the same source. So let's take a look at what that might look like. I'm going to do a different example here. So let's say that you had a NOR gate, and let's say that that NOR gate had the same source. Two inputs. Apologize for my... Okay, there we go. And T. So how would you do the truth table? You'd have A. And for simplicity or for ease of doing this, I'm going to put A again. Then T. Just because we have two inputs and they're the same thing. The only thing is, whatever this input is, this one has to be the same because it's the same input. So it can either be 0, 0 or 1, 1. It can't ever be 0, 1 or 1, 0, same input. So with a NOR gate, this is what we would end up getting as our result, and that's the final truth table. You can omit this second column if you like, or keep it in there, that's fine. But just know that it's just for your own, for ease of figuring out. There's another thing here, low and high. So low, remember we're dealing with electricity flow. Low means always off or 0. And high means always, well, the opposite, on or 1. So for the example, let's say we had an XOR gate. I know that that's not what the example is in the thing, but let's say we had an XOR gate and we had high, and then we had, so XOR, and we had a 0. So here's what the truth table would look like for that. So we have XOR, which is this, that's the symbol. So T equals, oh, so we have a T there. So here's the truth table. T equals 1 XOR'd with, and I want to just change this. I meant to put an A there instead of a 0. So A, okay. So we do have one input that will change from time to time. So A. I'm just going to look at my webcam. I'm going to pause this for a second. I'll be right back. Okay, I'm back, and I noticed that autofocus was on, but I turned that off. I think it's going to be better now. So 1, because that's high, XOR'd with A. A is going to be your input, and A could be... So I just did the truth expression. I didn't do the... So there's the truth expression. Truth table, which is what I meant to do. So let's do the truth. We had to do the expression as well. We'll come back to the expression for the first example in a moment. EG1, EG2. And this is just kind of like in a bubble. Okay, so example 2, we're doing the truth table. The first input is always high. We just put high there, that's fine. And then A is our second input, and then T is our output. So high is always going to be 1, and A can be either 0 or 1. Those are the only possible combinations of inputs. So with an XOR gate, exclusive OR, the only time you get a 1 is if exclusively one input is a 1. So we get a 1 there, we get a 0 there. That's the truth table. Let's go back to example 1 and do the truth expression, because I didn't do that. So T equals A, and this is a NOR gate. So the NOR gate looks like this, NOR'd with A. So that's the truth expression for example 1. So that's example 1 and 2. The rest of the, let's go to the browser now. The rest of the sheet, well, 1C is very similar. It just has low. Low is always off. Low always 0. 1D says explain in words how a NOT gate can be constructed using NAND gates. Just as a hint, what you'll do here is you'll look at what you did in 1A, B, and 1C, and you'll examine your truth tables. And you'll see if one of those matches up with the truth table for a NOT gate. If it does, well, there's your answer. That's the circuit that can be used to emulate a NOT gate using only NAND gates. NAND gates, as it said at the top, it said they're called universal gates, NAND and NOR, because they can emulate any of the 6 basic gates. In manufacturing, it is a lot cheaper to manufacture one single gate. So if they're trying to emulate a circuit or develop a circuit in a manufacturing process, it's a lot easier for them to just develop NAND gates. So they have a machine that can make lots of NAND gates on a microscopic level or a nanoscopic level. And what the engineers will do is whatever circuit they're trying to develop, they'll substitute all the other gates with NAND gates or NOR gates, whatever they're manufacturing exclusively, and then it's much cheaper for them to develop that. Hope I explained that okay. Let's look at it's just kind of a side note. Page 2 says construct a truth table, show the truth expression. So page 2 is taking what you've done on page 1 and combining it. So you'll notice that the second gate in 2A is a circuit from the first page. It's 1A. So 1A is the second part of 2A. Keep that in mind because that's going to be important later on. 2B, you'll notice that the first 2 gates that have A feeding into it and B, whether it's A or B, it doesn't matter. It's still, the whole fact is you've got a NAND gate with the same input for both inputs. The same input going into both wires of the inputs. So it's the same, both of those are the same as 1A. Keep that in mind because later on they're going to ask you a few things. So I'm going to leave this up to you guys. This is a thinking activity, this universal gate slab, and it does take a little bit of thought, but just trust me, it's all there. You have to look at what you've done on page 1, and that should really help you with page 2. 4A, now we're getting into the NOR gates, similar sort of thing. And same, it's very much like what came before with NAND gates, but now we're just using NOR gates. So do as much as you can. Maybe number 6 or number 7 will be a bit more challenging, but do what you can and submit it. And I'm going to give you the next thing on Monday. Monday, I'll have your midterm marks available to you on Monday. So that's it. Hopefully this helped out, and I'll see you next time.